Okay, we've had several missed class opportunities due to various activities. So we are going to begin by starting at the very beginning of chapter 13, which is on electric circuits. Now, one of the things we have to ask ourselves is, what is an electric circuit? Now, an electric circuit we build using wires and other types of basically metals and other materials. So one thing we could do is we could take a single battery, a light bulb, and just one wire, and we could try and get it to light. Now, there are several different ways we could do that, and we're going to get to a way that's correct and why it is correct. So when we start looking around us at our everyday lives, our cell phones, our computers, even something that seems as simple as a flashlight or your toaster, it all involves electric circuits and electric current. So if we were going to take a single wire to light up a light bulb with a battery, there are several configurations. And the main reason why the last one works, why C works, is that there has to be a complete path, a closed path. That path we call a circuit. So we have to have one complete closed circuit that our current can move across. So in this particular circuit, your battery is the energy source. Now there is a chemical reaction that separates positive and negative charges. That leads to a voltage difference with an excess of positive charges on one end and negative charges at the other. If you'll remember, all of our batteries are marked positive and negative for a reason. So these charges will tend to flow from one terminal to the other, provided we give it an external conducting path. It can't go inside, it has to go outside and around. That external conducting path is what we will call the circuit. So, backtrack a little bit. Electric current. If you can imagine that we put a gate across and we counted the number of charges as they came through, kind of like you do at like a concert, the number of charges that come through, or the amount of charge that comes through in a given amount of time, is the current. Now, we typically use the unit ampere, or amp, which is 1 coulomb per second, or coulomb is our measurement of charge. Now, what is going on here? You'll notice two different things. You'll notice that A shows a flow of positive charges going to the right, and our current is to the right. B shows a series of negative charges going to the left, but our current is still to the right. Now, if you remember from chemistry, what tends to flow is negative charges. But thanks to our good friend Benjamin Franklin, where positive is a surplus, the definition of current is that it is the direction of flow of positive charges. So that means the current, by definition, opposes the flow of negative charges, or our electrons. So that's why current is to the right. So remember, electrons, or our negatively charged items, are what is moving. So if we did a cross-sectional area of a light bulb, what we would see is there's a little metal tip here, and that's going to connect to a wire that goes to our little tiny filament that connects to another wire that goes to the side. Now there is an insulator between the side coils and this little tip at the bottom. So if you remember right, when we had this on the battery, this tip was touching the battery, and then we had a wire connected here that went to the other side of the battery. That allowed a full circuit. We could go from the battery up through this wire, through the filament, down to the tip, and back into the battery. That's what gave us that full path. So, in addition to an energy source and a conducting path, a circuit also includes resistance. In our flashlight bulb, this very thin filament wire is going to restrict the current. Basically, it's the equivalent of road construction on the interstate. It's going to slow everything down and make it a lot harder, kind of that traffic jam for electrons to go through. As a result of these charges forcing their way through there, the wire is going to get very, very hot. That is what creates the light, that glow. So here we have a couple of situations of light bulbs and batteries with wires. You'll notice that the first arrangement will actually light up because you are touching both wires that are connected in the light bulb and you've made a complete path. In B, there's not a complete path, so it will not light up. We often equate the flow of electricity, our electric current, with the flow of water. So we treat our battery like the pump. And the electric charge we treat like the water. Our connecting wires are similar to the big pipes. And the filament from the light bulb is similar to this nozzle constrictor right here. The switch would be like the valve, opens and shuts. So in a water flow system, the high pressure difference gives a larger rate of water flow. So we could increase that by raising the high tank to give it a larger potential energy. Similarly, if we have a large potential energy, a large difference in the potential energy between the charges at the two ends of the battery, we get a higher voltage and a greater tendency for the charge to actually flow, so a greater tendency for current. So here we have a situation of wires connecting a battery and a light bulb. The wood block would be completing the circuit. Now, wood, we kind of need to know whether it's dry or whether it's wet. Because dry wood is not a very good conductor. It's more of an insulator. If that wood is wet, it is an excellent conductor because of that water. So if the wood is dry, the light bulb does not light up. If the wood is wet, the light bulb would light up. So here we have an example of a circuit. Now, to give you kind of an idea of what some of these shorthand notations are, this is the symbol for a battery. The longer side is our positive side of the battery. This zigzag back and forth, that's a resistor. If we put a circle around it, this is a light bulb. So the question is, we have a light bulb connected to a battery. If we put a wire just from point A to point B, do we increase the brightness of the light bulb? Well, our current is going to get to point A and it's going to have an option. It can either go down to go straight to point B, or it can go to the right and go through the light bulb. Current follows the path of least resistance. As such, what we do is we connect that wires and we create a short circuit. The battery will actually get damaged and there will be virtually no current going through that light bulb. So it will actually decrease the brightness of the bulb. Now, if we look here, one thing to note, there is no completion of the circuit on this battery. there is not a line coming into that short side of the terminal, so the negative side of the battery is not connected. Over here, we do have an open switch, but we have a full path going all the way around and back to the back side of the battery. So the second arrangement has a full closed circuit, therefore it will actually light up. Now, if we get the idea to use a C-clamp to hold the wires onto the battery, that will not be very effective because that metal clamp is going to provide a large path. It's going to be almost like an expressway for electrons to travel on versus the small little 2-lane wire. So we will have a large amount of current going through the clamp. If we wanted to use something like this, we would need to put some sort of an insulator above the wire but below the C-clamp in order to keep the electrons from flowing into the C-clamp. This leads us to the idea of Ohm's law. Ohm's law basically says that the electric current flowing through a specific portion of the circuit is proportional to the voltage difference across that part of the circuit and inversely proportional to the resistance. And you may be saying, but what is resistance? Well, if we imagine blowing through straws, if you take a coffee stirrer, the little bitty thin straws, and you take a regular drinking straw, and you take a cardboard tube from a paper towel, and you try blowing through those, you will quickly understand what we mean by resistance. What we're talking about is we're talking that restriction to flow. If we blow through a cardboard tube, air is going to flow through just fine. If you try the coffee stick after that, you will notice a big difference because the coffee stirrer will have a larger resistance to that airflow. So, resistance is going to be the ratio of the voltage difference to the current. It is always given in units of ohms. So this is where we get all of our ohm jokes from. Now, wires themselves do have resistance. We typically, at this level of physics, do not calculate it as such, but there is resistance in the wire. That resistance is proportional to the length of the wire. It's inversely proportional to the cross-sectional area. Also, the conductivity of the wire plays a part. So some materials are more conductive than others. Electrons flow freer, therefore they have a lower resistance. So temperature will also play a part because some temperatures will restrict the flow of charge. Now here we have a couple of signs that are kind of concerning. The one on the left says, danger, 100,000 ohms. The one on the right, danger, 10,000 volts. Now, 100,000 ohms, that's just resistance. We can find resistors just laying in drawers. They don't have to be necessarily connected to power. The 10,000 volt one should seriously concern us because that has the potential for serious bodily harm. So the one with the ohms, that's more of a joke. It's kind of a practical joke. The other one is a serious warning sign. So if we have the resistance of a given portion of a circuit and we have the applied voltage, we can calculate the current through that portion of the circuit. So here we have a 20 ohm resistor and a 1.5 volt battery. So we can use Ohm's law that delta V equals IR. So we're going to veer. So the change in voltage across this, or the change in voltage across the circuit, so the 1.5 volts, is going to equal the total current times the resistance, which is 20 ohms. And so that's how we can find the current. The current is going to be 1.5 over 20, which is 75 milliamps. Now, that was assuming that the battery did not have any resistance internally. That is not the case. If the battery is fresh, the internal resistance is very small. We can often ignore how large it actually is. As the battery gets used, that internal resistance will get larger. Eventually, it gets so large that the battery is essentially what we call a dead battery. It's not working anymore. We call the voltage of the battery the electromotive force, E. And so we use a different version of Ohm's law, that the electromotive force, script E, is going to equal the total current in the circuit times the total resistance in the circuit. So we call that the Erie equation. It's also known as the loop equation. So here we have two resistors. These are in series, and I will get to what that means. And what we're going to do to calculate their total resistance, since they are in series, is we're going to add those two resistances together. So we get that the total resistance of the circuit, the equivalent resistance, is 25 ohms. So that means that the current, we're going to take the 1.5 volts of the battery, divide it by the 25 ohms in the circuit, and we're going to get that the current is 60 milliamps. So that means the voltage drop across the battery is going to be 1.2 volts. So that means that this resistor inside the battery is taking up 0.3 volts. So if we disconnect the bulb and we measure the voltage across the battery terminals again, we're going to get 1.5 volts. We have to have a full path. The total resistance of the circuit is going to increase and reduce the current flowing as the battery gets older. As the current gets smaller, as a result of this, that batteries, the light itself is going to get dimmer. So when we call the battery a dead battery, the internal resistance is so large we can't really get a measurable current off the battery. A voltmeter is connected across an element of the circuit. So it would be connected across the battery, just like the symbols here show. So you'd have one terminal here, one terminal here. It's connected across an element. It has a very low, or it actually has a very, very low current going through it. So it has a very high resistance. What it is trying to do is just measure the voltage drop across this element. So that leads us to the idea of series and parallel circuits. In a series circuit, essentially the elements are holding hands. There are no branches, no turns. Everything is on one primary loop. That is a full series circuit. You have one single loop. The current that passes through one element has to also pass through the others. There's no side roads for it to take. So if we have several resistances on that loop, we add all of those resistances up in order to get the total resistance for the circuit. Now, the current will stay the same. The current will not get used up. The same current has to flow through each element of a series circuit. I repeat, the same current has to flow through each element of a series circuit. However, the voltage changes as the current flows through the circuit. It will decrease based on Ohm's law as the current passes through each resistor. So the total voltage difference across the combination is the sum of those individual changes. So if light bulbs are connected in series with the battery, the current is going to be less than the single bulb because the resistance is larger. Since the current is less, the bulbs are not going to be as bright. So here we have two resistors that are in series. Since they are in series, they have the exact same current flowing through each one. Now, if we know that resistor 1 is less than resistor 2, by Ohm's law, that tells us that the voltage difference across resistor 2 has to be larger. So here we have a battery. This is an example of showing a battery with an internal resistance. And this internal resistance is 1 ohm. And we want to know what the current is that's flowing through the 9 ohm resistor. So the first thing we have to do is we have to find the total equivalent resistance. The total equivalent resistance is going to be 1 ohm plus 9 ohms. Because they're in series, we would add the resistance, so that's going to be 10 ohms. We're then going to take the total voltage, which is the 3 volts of the battery, divide it by the 10 ohm, and get that the current is going to be 0.3 amps. Now, with that current being 0.3 amps, if I want to know the voltage drop across this 9 ohm resistor, the change in voltage is going to be the total current times the resistance. So it's going to be the 0.3 amps times the 9 ohms, which is going to give us 2.7 volts. So here we've got 3 resistors, a 15 ohm, a 20 ohm, and a 25 ohm resistor. They're in series. So that makes the total equivalent resistance 60 ohms. To get the current that's going through the circuit, we take the total battery voltage, 6 volts, divide it by the total equivalent resistance, which is 60 ohms, and we get that the current is 1 amp. Now, the current that leaves the battery is 0.1 amps. That means that is what has to travel because it can't go anywhere. It's got to just keep traveling through the same locations again and again and again. So 0.1 amps is what goes through that. And so, yes, the same current is going to flow through each element in the series circuit. If we're going to find the voltage difference across the 25 ohm resistor, we're going to use Ohm's law, delta V equals IR. Since I is 0.1, that means that the voltage drop is going to be 2.5. Now, we could also look at parallel circuits. In the parallel circuits, there are options. So here you have an example of 3 light bulbs in parallel. So when the current gets to this point, it has an option. Does it want to continue this way or this way? Here it has an option. Here the current is going to be coming back together, and here the final current comes back together and then goes back out. So we have a current split. It will then later rejoin. The total cross-sectional area the current flows through is increased, therefore it's going to decrease that resistance. That's like holding multiple straws together to blow through. So we find the equivalent resistance using the inverse of each of the individual resistors. That's going to equal the inverse of the equivalent resistance. In parallel, the voltage difference across the elements that are in parallel are the same. So this change in voltage is equal to this change in voltage is equal to this change in voltage. And that's because they're connected between the same 2 points. They have to have the same voltage drop. That means that the currents can be different. Because the currents split up, they can be different. And we're going to get a portion of the current going through each individual branch. So what we get is that parallel combinations are going to decrease the resistance and therefore increase the amount of current. That causes light bulbs to burn brightly, but it also depletes the batteries quicker. The energy that's available from the batteries would be the same in the case of either circuit. So here we have 2 10-ohm light bulbs that are connected in parallel. If we wanted to know the total current flowing through the loop, first we would have to find the equivalent resistance. So since these are both 10 ohms, we have 1 over 10 ohms plus 1 over 10 ohms, which is going to equal 2 over 10 ohms. Now that's equal to 1 over the equivalent resistance. So the equivalent resistance, we're going to flip it, and that's going to be 5 ohms. We would then use the loop equation, that the 6 volts that are applied divided by the 5 ohm equivalent resistance gives us a current of 1.2 amps. Now what's going to happen? This 1.2 amps is what we have going to this point. At this point, the current has to decide what's going on. And that current is going to split in such a way that the voltage drop across each element is going to stay the same. So what we know, since the resistance is the same, and the voltage drop is the same, the current is going to be the change in the voltage over the resistance. Since these two are the same, that means the current has to be equal. Well, the only way it can do that is if it's half of what we started out with. So that would be 0.6 amps. Here we have 3 identical resistors. The first thing we want to do is find an equivalent resistance. So we're going to use the parallel equation, 1 over 24 plus 1 over 24 plus 1 over 24. That's going to give us 3 over 24. We flip that to find the equivalent resistance without the inverse. That's just going to give us 8 ohms. So I could redraw this circuit as having a 12-volt battery and just an 8 ohm resistor, and this would be an equivalent circuit. So my current, my total current is going to be 1.5 amps coming in. Since these resistors are all the same, it's going to split evenly. So this one's going to get 0.5 amps, this one's going to get 0.5 amps, this one's going to get 0.5 amps. So you would have an even split. Now, if we're going to look at the total current through the combination, we would use Ohm's law. And you can ignore these, they're the wrong units. So Ohm's law says our total voltage divided by our equivalent resistance is going to equal our current. So we get 12 volts divided by 8 ohms, which gives us 1.5 amps. If we're wanting to know the current that's going to flow through each resistor, this 1.5 amps is going to split. And since these resistors are all the same, it's going to split evenly. So each resistor is going to have 0.5 amps of current. So again, ignore the units over here. And here. Now here we have a circuit where R3, resistance 3, is greater than R2, and R2 is greater than R1. So R3 greater than R2 greater than R1. We have the electromotive force of the battery, and we want to know which of these resistors has the greatest current flowing through it. Well, think about what's happening here. We have a current, it gets to this point, it's going to split, comes down here, it comes back together, and then it goes through R3. So since all of the current goes through R3, that's who's going to get the biggest current. It doesn't matter who's the bigger resistor. What it matters is their position in this circuit. That leads us to meters. A voltmeter is going to measure the voltage difference between 2 points in the circuit. We always put that meter in parallel. It has a very, very large resistance, so that very little current is diverted. And that allows us to measure things with a little bit more accuracy as regards to the voltage. So here we have a voltmeter in a circuit, and we want to know which statement is correct. Now what's going to happen is that this is actually the correct position for a voltmeter. It's measuring across the resistor R. It should always be in parallel with its units. Now conversely, an ammeter has a very, very low resistance. It is put in series so that the current flows through it because ammeters measure the current. If you get the idea to put an ammeter directly across the terminals of a battery, you could damage both the battery and the meter. It is not uncommon for fuses to get blown. We have to be extra careful. This is why we don't power on any circuits without checking first. So in this particular picture, what we have is that the ammeter is a low resistance. So if we put it in parallel like this is showing, we're going to draw pretty much all the current through it. So this is not in the correct position.